there. Okay, so in this first lesson, we're going to show how do we get the derivative of an exponential function, and we're going to look at one particular function, a special function. So don't write this down. We're just going to walk through to understand, well, why is the derivative, why it is what it is. What is it? To help understand why it is what it is. Okay, so here's our generic exponential function. Y is equal to b to the power of x, where of course b is some base value that's greater than 0 and typically not equal to 1, right? Because otherwise you don't have any growth or decay. So in order to find the derivative, we're going to use our good old-fashioned first principles to sort of see what's going on here. So the derivative of this exponential function is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. So the h was usually the easiest thing to put down. F of x is the next easiest thing to put down. And then f of x plus h. So that's going to be b to the power of x plus h. Okay, so that's where we start. Of course, if you substitute h, 0 in for h, you're going to get 0 over 0. Right? So of course that always means it needs some more work. All right, so the question is, well, what kind of work can we do here? Well, considering it's an exponential function, we're going to apply some exponent laws. What kind of exponent laws do we know? Well, we know that if you multiply powers that have the same base, you add the exponents. Oh, well, that's great, because I see the sum of x plus h. Well, that means we should be able to break that apart into b to the x times b to the h. If we make that look a little bit more like an h. Right? Because that should combine to give us b to the x plus h. Okay, minus b to the x all over h, which means we can factor that top, right? We can factor the top and pull out limit as h approaches 0 of b to the x and then b to the h minus 1 all over h. And you might say, okay, so what? Big deal. Well, here's the thing. What's b to the x? If we put h in there, what happens to b to the x? The answer is absolutely nothing, right? Because b to the x is just some number. Right? It's just some number. No matter what h is, b to the x is just some number, right? Because there's no h attached to it. So what we can do is, because that's just some number, we pull it out like a coefficient. So this derivative is going to be b to the x times the limit as h approaches 0 of b to the h minus 1 over h. And now this is kind of where we're going to stop. And you're kind of like, great, we're stopping. What do you mean we're stopping? We haven't found anything else. And the reason we're going to stop is because this piece here poses a question. What is this? How much is this? What is it? So to answer that question, you're still not writing anything down. Good. We're going to walk through it. In other words, what is the limit as h approaches 0 of b to the h minus 1 over h? Well, here's what we're going to do. We're going to use our calculator and we're going to test some values. We're going to try, what if b is equal to 2 and what if b is equal to 3? So this means these are values for b. Okay, so take out your graphing calculator. This one you can do. When b is equal to 2, let's see what this gives us. Okay, so remember, what we're going to type in is we're going to type this into y1. We're going to type in y1 equals, what do we want? We want y1 is equal to, so 2 to the power of x minus 1 over x, and then we want to look at our table and see what happens as it gets closer and closer and closer to 0. All right, so this is a little old stuff. So I want, in brackets, 2 to the power of x minus 1 all over x. Okay, so that should give us 2 to the power of x minus 1 all over x. And we're just really interested in the table, so let's see. What's our table setup? Starts at 0, goes by 1. Perfect. All right. So what we can see there is that, well, I'll take a couple of pictures here. That sort of balances it out. Coming at it from the right-hand side, 2.3 repeated, 1.51. And from the left-hand side, 0.29167, 0.375, 0.5. And then at 0, there's an error. So that means, obviously, it's getting closer to some number. I wonder what that number is. So we'll take a little screenshot, just a little thing there, and paste it. So that way, let's do this. Okay, so this is b is equal to 2. We're going to do this again by shrinking the table. We're going to start at 0, and we're going to go up by 0.1 this time. And take a look at the table. Okay, so you can see that coming at it from the right, oh, we've dipped below 1 now. And coming at it from the left, we've gone a little bit higher than 0.669. So we must be higher than 2/3 already, right? Because 0.6 repeated would be 2/3. So this is getting a little higher. So again, let's just copy this little picture, paste it, make it a little bit bigger, and let's do one more time. Okay, so one more time. That means we're going to go to the table, start at 0, and go by 0.01 this time. And hit the table and kind of scroll up. And it's, well, it's getting close to 0.69 something, right? It's getting close to 0.69 something. It's like, okay, so what? Right? Really not much there. So this limit, as h approaches 0, of 2 to the h minus 1 over h is getting close to 0.69 something. And I'm going to just paste that one last, oops, that's not what I wanted. No, I don't want to close it either. Take this picture and let's paste it one last time. Okay, that's kind of interesting. Now on the right-hand side, we're going to do, well, what happens if b is 3? Okay, so that's b is equal to 2. What if b is equal to 3? Let's use a different color now. So if b is equal to 3, y is equal to 3 to the power of x minus 1 over x. Okay, let's just quickly walk through. Y is equal to 3 to the power of x. So we're looking at these just a couple of different exponential functions, right? 2 to the power of x. And now 3 to the power of x. So if I change my table set to 0 and 1, right, if I change it to 0 and 1, from the right-hand side, okay, 8, 4, 2, and then from the left, 0.3, 0.4, 0.6 repeating. Well, and that negative 1 there is, that's 2/3, right? You can see that. So at 0, it's got to be something in between 2 and 2/3. All right. And so take a quick shot. See, and there's no way that you could write all this down. So thank you for indulging me and just watching. So now let's zoom in. So change this to go by 0.1. And now you can see that, okay, so this is a little interesting, right? For 3, it appears that we're approaching a number that's actually bigger than 1, right? When we used the base of 2, it was approaching what appeared to be about 0.69. This time now, it's approaching something greater than 1. All right, so let's just sort of take that screenshot there and paste it and bring it over here. And we'll do one more, our usual, same old, go to the table and change it by 0.01 and zoom in, and you get a better picture here. It's just a teeny little bit more than 1, right? 1.09, 1.1, somewhere in there. So we're getting close. All right. And so again, what this is basically saying is that the limit as h approaches 0 of 3 to the h minus 1 over h is about, call it 1.1-ish. Right? So that when we look at the derivative, here's basically what we're looking at, or what we're seeing so far, is if y is equal to 2 to the x, what's the derivative? Well, based on what we saw here, the derivative, first of all, starts with the original function, b to the x, right? Because it gets pulled out as a coefficient. And then it gets multiplied by something. And it's this something that we're investigating here. Okay, so what's the limit, or sorry, what's the derivative of 2 to the x? Well, it's going to be 2 to the x times, well, about 0.69, right? But something more specific, something more precise. What's the derivative of 3 to the x? Well, the derivative of 3 to the x is going to be 3 to the x multiplied by something. And this something is about 1.1, right? So it appears the derivative of an exponential function in part involves an exponential function, but the real key is, what is this? What is this? And so here's kind of where the next question moves to. The next question says, the simplest differentiation formula would occur when that whole thing becomes what? 1, right? The simplest thing would be if this could become 1. Because here's what you'd have. You'd have y is equal to something to the x, and then what it produces is that something to the x times 1. That would be just great, wouldn't it? Right. And so now the question is, which value of the base is used so that when you take its derivative, you get the exact same thing? That's the key question. Anybody want to take a guess? Not 0. Clearly, it's between 2 and 3, right? Because 2 gives us this 0.69. 3 gives us 1 point something. So I think the number's between 2 and 3. And it's closer to 3 than it is to 2. So the question is, what is it? Well, it's E. Like, oh, great, where'd that come from, right? E is the base, okay? E is the base such that the limit of e to the h minus 1 all over h is equal to 1. Now, take a look at this, and we'll kind of work with this in a minute. Go to your, whoops, quit. Hello. On your calculator, do you see where the letter E is? You have an E, see? You got an E there. You haven't seen that E before. Second function, and then the division symbol. What happens when you press enter? Hey, it's 2.718, right? And so this is an irrational number, all right? This doesn't repeat. It almost looks like it does, but oh, maybe no, it doesn't. I don't think it does. I don't think it does. Do you think it does? We'll double check that. But you can see that this is the value. It's between 2 and 3. It's between 2 and 3, right? And obviously it's closer to 3. And so this is the value so that when we take the derivative of this function, right? F of x is equal to e to the x. If you take its derivative, you're going to have e to the x, and then the limit of that particular thing there, as h approaches 0, of e to the h minus 1 over h gives us the 1. And so this is really kind of cool. The derivative of the function is the function itself. Right? It's like, what? What? Well, here's a thing that hopefully helps us remember, or kind of, or make sense of it. We're looking at an exponential function, right? And you kind of know the characteristics of exponential functions. So down here, got a little picture, remember. Remember that the slope of the tangent line to a point on the curve, whatever the value of that slope is the numerical value, right, of the derivative. Well, exponential function, if you just kind of think about it, here to the left-hand side, the slope is rather shallow. In other words, because the slope is rather shallow, it's positive, but it's low, it's close to 0. And then the further you move to the right, the greater the slope becomes, and so, of course, the steeper the line gets. So their derivative values almost match. Right? In fact, if you take a look at, so I've kind of got it here, if you take a look at y equals 2 to the x, okay, so first of all, if I punch in here, y is equal to 2 to the power of x, right, that's our original function. So the derivative will basically be, if I take the derivative at the different value or different places, different x values along here, the value of the slope becomes the new points for this, for the derivative. Well, what does the derivative look like? If I click on it, am I on it? I don't know if I'm on it. And I go, let's see the derivative. And you see the black line? It's pretty close. Right? In other words, if I've got 2 to the x, and I'm looking when x is equal to 0, what's the slope of the line on 2 to the x when x is equal to 0? It's just a little less than 1. Right? In other words, the slope's not quite there. And if I take a look at 3 to the x, so y is equal to 3 to the x, okay, so it's a little steeper. And then I say, well, what's the derivative of 3 to the x? And you see that it jumps above now. Right? So that the derivative, especially if you think of when x is equal to 0, the slope of the line there is a little steeper than 1. Okay? And you see how close they are. So now, if I punch in y is equal to e to the power of x, okay, so that's our line. And now when we find the derivative of this line, yeah, all it does is change color because the derivative is the exact same thing. Huh. Oh, okay. So, and so that's basically what we see there. So now the only thing is, all we've discovered is one special exponential function, namely when the base is e. So if you're looking at your formula sheet, right? You're looking at your formula sheet and you're looking for the derivatives, you see there's a section on exponential and logarithmic functions. And you see d dx of e to the u. So it's like, well, the first one they give us is with this e. And then you see it's got e to the u multiplied by du dx. Okay, because of course you have to apply chain rule anytime that you've got something funny going on there. But if you look at the one beside it, right? If you look at the one beside it, this is now, well, what if we want to talk about b to the x? What is the true derivative of y equals b to the x? Okay, so I'm going to talk about that, and I'm going to go back to, remember this number here? Where did that number come from? Where did this number really come from? And why is it that when you're looking at deriving e to the x, that you get a 1? Right? So the question is, well, what's kind of particular about this value? Now, if you want to write something down, one of the first things you want to write down is, well, basically this. If your function is e to the x, the derivative becomes e to the x. Or I think actually this page, here's where you want to write it. In general, the derivative of e to any power is equal to e to that power, and of course multiplied by the derivative of that power where that exponent is a function of its own. Okay, so that's kind of the first thing. And what we've done is basically walked through to see Why is the derivative of e to the x just e to the x? Because e is that special number. Well, now what we're going to do, and again, you don't have to write this down, but I'm going to walk you through this little block exercise here. Shows sort of, well, what about any function? What about 2 to the x? What is the derivative of 2 to the x? And don't just say that it's 2 to the x times by about 0.69. The key question is, what's that 0.69? Where is it from? Okay, so I'll kind of just walk through here. Okay, if I start with y is equal to b to the x, okay, so kind of watch what happens here. Oh, look at that. That second line, notice what we did there. We kind of did a little sneaky thing, right? And this is what mathematicians get paid the big bucks for. I'm a teacher. I'm not a mathematician. Well, actually, I'm a mathematician. Mathematicians get paid the big bucks to sort of a little sleight of hand work, right? Notice that this b has now been replaced by this expression, e to the power of the natural log of b. And you're like, wait a minute, e to the natural log of b? Well, do you remember, if I've got 2, well, actually, let's do it this way. If I've got 10 to the log, base 10, of 3, do you remember what this is? It's 3. Okay. Right? And this comes from 30-1. Right? So this is why we're sort of remembering the logs, and the people that said, yeah, they're the ones that just wrote a logs exam earlier today, right? If your base of your exponent matches the base of that logarithm, right, in a sense, it's not that they cancel out. Don't like to use the term cancel out. But they can be changed, the form can be changed so that you see that this is what you get. You get 3. Right? You remember nothing. Okay, so here's where you kind of go back to this one here. It's kind of like this one here. Actually, this is exactly where it comes from. If you have the natural log of e to the x, this is like saying, what is the log base 10 of 10 to the power of 2? Right? What's the log base 10 of 100? Well, you know that the exponent law basically says do this. This becomes 2 log of 10 base 10, which is 2 times 1. Right? Anytime that your base of your logarithm matches the base of your exponent, the value is, in a sense, that exponent there, right? And so the natural log of e to the x, this is going to be x times the natural log of e, which is going to be x times 1, right? Because that's 1. And so in its exponential form, if we can match e and this natural log up here, we get the same thing. It comes out as x. Okay. Now, where we're going with that, remember, is kind of back in our looking at the base, sorry, the derivative of any base, the exponential function with any base. Okay, so we replace this b with e to the natural log of b all to the power of x. Now, what we're doing next is, this is a power, right, e to something, raised to a power. And what do you do with those exponents when you have a power to a power? You multiply the exponents. So that's why this next line is e to the natural log of b times x. Okay, e to the natural log of b times x. Okay, now here's the thing. E to the natural log of b, all right, or sorry, wrong place. This natural log of b piece up there, that's just some number, right? The natural log of b, that's a number. And then, of course, the x is there. So it's kind of like saying, here's an example. If y is equal to 3 to the x, this is kind of like saying y is equal to the natural log of b times x. Kind of, right? It's not exactly the same, but it's like that, right? It's just some number. So when I take the derivative of 3 to the x, or sorry, if I take the derivative of 3x, what's the derivative? Well, it's just the 3. So if I take the derivative of something times x, what's my derivative? Well, the derivative is just that something. Okay, natural log of b. So at this point, and by this point I mean this point, if y is equal to e to the power of something x, using this rule, I'm going to get e to that something that we had multiplied by the derivative of that u. And the derivative is simply natural log of b. Huh. And then notice all I'm doing is I did this sleight of hand at the beginning, and all we're doing here is we're doing the same sleight of hand back. Okay, b was replaced initially with e to the natural log b. And so all we're doing down here is we're taking e to the natural log b, taking it out, and then that makes b to the power of x. Okay, now you might say, well, so what does that do? Well, basically, I'm going to link this back to the base of 2. Okay, so in other words, just as an example, if y was equal to 2 to the x, what should this derivative be? Well, according to what we've just done here, the derivative should be the same thing, 2 to the power of x, multiplied by natural log of that base. In other words, the natural log of 2. Now, any wild guess before you touch your calculator what the natural log of 2 is? 0.69. All right? Remember that 0.69? The limit as it was getting closer? It's like, where did that come from? What does this represent? Well, what I think we've just discovered, or not discovered, but what I hope we've seen is, what's the natural log of 2? In other words, what exponent do you put on the letter e to get a value of 2? Look at that. It's 0.69. In fact, when we kind of zoom in on here, you can sort of see, right, where the error is. 0.693. Oh, that makes sense. So that numerical value, that limit piece that we've been evaluating, is actually the natural log of that base. Any wild guesses as to what the natural log of 3 should be close to? Right, 1.1. There it is, right? Yeah, now it's close, right? 1.098612289. So that's where that number piece comes from. Now, I mean, I do, but I don't. I don't apologize. That I hope what we've done is by developing this, you understand where the pieces of the derivative come from. Okay? And so if you want, you can watch this video again, maybe put yourself to sleep again, maybe again. All right? And you discover now where this E comes from. All right? What this letter is. And again, it's the letter so that when you look at its exponential function and you take the derivative, you get the exact same thing back. Right? And so in general, you have the derivative of the exponential function with a base of e. That's on your formula sheet. The chain rule, of course, applies. And then down here, and again, this is also on your formula sheet. What's the derivative of any exponential function? So any base, it's any base. So it's that exact same thing multiplied by, don't forget, the natural log of the base, because that's the only piece that's different, because here you don't have that. The reason you don't have that is because the natural log of e is 1. And then you don't forget your du dx. Okay, so that's where that derivative comes from. Okay, so it's on your formula sheet. And, you know, maybe if I were a lesser teacher or a better teacher, I don't know, we'd just say, okay, here it is on the formula sheet, let's go. You know, and we could have saved ourselves 45 minutes. But I hope you have a better understanding of sort of, you know, why it is what it is. Why are there all those kind of component parts to it? And then basically all we're going to do is we're going to just look at a couple of examples of these exponential functions. So we've got sort of 4 there, and then we've got, I guess, a few more there, and then we've got one of our favorites, find the equation of a tangent line, and then find max and min, and if time permits, I don't think we'll have time. But basically, now that we can derive this type of function, exponential function, we can basically do everything that we've done up to this point in the whole course, right? Finding intervals of increase and decrease, finding concavity, all that stuff should be able to do. Okay. I'm just going to pause, see if there are any questions. You are. Okay. Can you what? Oh, go over your tests? Well, let's do some examples, and then I'll leave some work and we can go over some tests. All right. So, example number 1, find the following derivative. We've got y is equal to, so if it helps, change this to this. All right? Y is equal to 5 to the power of u. Nice. So the derivative is going to be, well, it's going to be 5 to the power of u multiplied by the natural log of the base, so of 5, multiplied by du dx. Right? So remember that when you're deriving an exponential piece, there are always, in a sense, 3 pieces. The exact same thing you started with, the natural log of the base, and the derivative of the exponent. Okay? And so now, yeah, ln, right there. So this is going to be 5 to the power of 2x times the natural log of 5, and you leave it as the natural log of 5, because that's an exact value. Don't change it to a decimal, right? Leave it as natural log of 5. And then multiply this by, well, du dx, so in other words, the derivative of the exponent, so by 2. And so now, here's kind of the thing is, well, none of these really simplify in any way, shape, or form, because we've got a 2, we've got a 5 that has an exponent, and then we've got a natural log of 5. So all we're going to do here is just maybe put the 2 in front, 5 to the 2x, and then the natural log piece, typically I put at the end, right? Because then that way I don't have to worry about putting a bracket around the 5. Whereas if I put the natural log piece earlier on, right? Because even here, it kind of looks like, should I be multiplying that 5 and the 2 together to get a 10? Okay, and the answer, of course, is no. Right? So that's typically why I'll put the natural log piece at the end. These are all prime specimens, yes. Thank you. Forgot about that. Okay, so that's the first one. All right, do you want to try these next 3 while I hand out your tests? I knew you'd say sure. Okay, next example. Y is equal to e to the power of the root of 3x. So again, think of this as y is equal to e to the u, so that the derivative is going to be, well, first of all, it's going to be that same exponential piece multiplied by the natural log of the base, which in this case is e, which will be nice, multiplied by the derivative of u. And so now let's piece those together. Well, what is e to the u? Well, it starts with e to the root of 3x. What's the natural log of e? 1. Multiply that by du dx. So what's the derivative of the root of 3x? Well, now here you kind of have to maybe off to the side a little bit. Think to yourself, okay, well, root of 3x is 3x to the 1/2. And so the derivative of that is going to be 1/2 3x to the negative 1/2. And don't forget to multiply by the 3 inside yet. Wow. Yeah, so there's a lot of stuff there. So this is going to be, and then this 3x piece is going to come down to the bottom. So this is going to be 3/2. And then on the bottom, you're going to have the square root of 3x. So simplifying, in a sense, all of that, the derivative is going to be 3. We can kind of worry about the 1. E to the root of 3x all over 2 root of 3x. What's that? Yeah, they don't, right? Because one is in the exponent, the other one is not. And in terms of, well, what does this function look like? Man, we've never seen this function before, right? It's kind of like wild. It's wild stuff. So you're doing some really powerful kind of stuff without even kind of knowing what the graph looks like. All right. Uh-oh. What do we got in C? Oh, we've got a product rule. So yeah, don't forget the product rule, right? So everything that we've learned up to this point, we put back into practice. So product rule, let me use green just to kind of alternate some colors here. First times the derivative of the second, second times the derivative of the first. Yeah. Right, so the first is x to the fifth. The derivative of e to the x is going to be e to the x times the natural log of e, which is just 1, times the derivative of x, which is just 1. Sweet. Yeah. So that's why if it's just e to the x, it's really simple, e to the x. All right, plus the second, which is just e to the x, times the derivative of the first, which is 5x to the 4. And this is why we learned this back in pre-calculus. We got a factor. Take out the common factors. So we've got a factor of e to the x that's common, and an x to the power of 4 that's common. Okay? And in terms of which one you put first, doesn't really matter. I'm going to pull x to the 4, e to the x, and then that's going to leave us with x plus 5. And now, because now that we've kind of got this factored, it means that we could also tell where should the critical values be. You don't want to know. Well, where is it 0 or undefined? Well, when you look, it's just a nice product, right? E to the x is what? Yeah, right? E to the x is your exponential function, and your exponential function is always giving you a y value that is above 0. So you never have to worry about the e to the x part. The only part you have to worry about is x to the power of 4, which is also always positive. The only thing you really have to worry about is that factor of x plus 5. Right. And then you can sort of do your interval pieces and sort of say what's going on there. So you've got the tools, right? It's just a matter of the process is kind of getting a little longer now, and it's involving some stuff that's maybe a little less familiar. But you can do that, right? But yeah, what it kind of took there is just understanding that e to the x is always going to be positive, right? That's kind of nice and helpful. All right, this last one here is actually, it's a little bit different. And so if we kind of, again, just sort of break this apart, this is, our original function is y is equal to 7 to the power of u, where u is 7x. Or is it u are 7x? All right. Okay, just messing. All right, because u, what is u? U is 7x. But grammatically, shouldn't it be u are 7x? Not really. I know, but didn't we have this discussion? Was it this class or maybe it was a different class about, kind of poor grammar? Heard it again on the radio. I think it was this morning or yesterday, some expert in something, and she's talking and she uses is with a plural, and I'm like, oh, they always say, that the way you communicate, it's a prejudice. It's a bit of a prejudice, but when you sound intelligent, people kind of automatically assume that you are, right? For better or for worse. And so when you don't sound intelligent, people, again, automatically assume that you're not. Yeah. Well, I don't know about that. No offense to anybody out there listening to this YouTube video that's maybe from the South. Yeah, but we up here in Canada, redneck Edmonton territory. Ooh. Okay, so the derivative. The derivative is going to be, well, the exact same piece multiplied by the natural log of the base multiplied by the derivative of u with respect to x. So y primed is going to be 7 to the power of 7x times the natural log of 7, which we have no clue what that is, so we leave that, multiplied by, what's the derivative of 7x? 7. Now, this particular example can actually be simplified. Okay? Mostly because here's what you would kind of think of doing. You'd kind of think of pulling that 7 to the front, and then you've got 7 to the power of 7x. And then you've got the natural log of 7. But those two guys there, right, are the same base. Yeah. So we add the exponents together, 7 to the power of 7x plus 1, right? The 1 really comes from there. That's exactly right. And that's kind of why we have this example here, is because it's just a teeny little bit different. So when the bases are the same, which is what you have there, right? Same bases, add those exponents. Right? All right, well, let's all right, let's do these three, and that's probably where we'll call it a day. And then you can begin working on the homework. The last two examples are the one about finding the equation of a tangent, but you've got all the tools necessary for that. Even the last example is find max and min in intervals of increase, decrease. Again, you've kind of got all the tools of that. So I want to make sure that you just give yourself some time to practice that. Now, also, just so you're aware, this today's what, Wednesday? Okay, lesson number 1. Tomorrow, lesson number 2 will be derivatives of logarithmic functions. So it's kind of like the other half. And then Friday's a shortened day. And I'm not here Friday. So there will not be a lesson Friday in terms of learning anything new. So use that time to let's see, to kind of catch up on homework. Well, no, good question. So Friday will be a work day. Monday, we're going to be doing the logarithmic differentiation. Okay, so it's something new there. Tuesday is our review day, and then Wednesday is the day of the exam. Okay, so that way at least you get some time to hopefully work on some of the other types of problems here. All right, example number 2. Again, some more, just find the derivative of these expressions. We've only got 3 of them, but we've got some trig now in there. Ha! Oh boy. Sammy's shaking her head. Don't like the trig. Not combined with the exponential function. No, not at all. Okay, so let's take a look at the first one. Let's just move the other one down a bit. Okay, so y is equal to the sine of something. So what's the derivative of the sine of something? All right, it's the cosine of that something. Now, it's the cosine of that something multiplied by the derivative of that something, right? So kind of just process slowly that chain rule. What's that something? Oh, that something is e to the x. And so now what's the derivative of e to the x? Oh, well, that's kind of nice. It's just e to the x. And so, whoops, I guess what I would like to do is, on a new line, what should our derivative look like? Here's again why we use the square brackets for that derivative. Move it in front so that you've got the cosine of e to the x here. And what you may see, oftentimes you will see this like this. All right, and I'm more of a fan of putting the brackets there. It's just, I think it just keeps it a little bit easier to see. All right. Don't let it get away. Don't let your ex get away. Oh, that doesn't sound quite so good. Let your ex get away, right? Isn't that the Michael Bublé song? You ever heard that song? It's a beautiful day. We're kind of like, that's such a nice, happy song. And then you listen to the words, it's like, wait a minute. It's a beautiful day because you're gone. I'm like, wow. Let your ex get away. Yeah, we got 2 x's. One is inside the cosine, the other one's not. The other one is cos to you. not far from you. She's close to you, or he's close to you. The puns just keep on rolling. You can tell I'm feeling much better now. Not coughing as much on the videos. Okay. So, yeah, we're done there. Let's put a little box around it. Okay, so y is equal to e to the something, right? E to the something. So what's the derivative of e to the something? It's e to the something multiplied by the natural log of e. Okay, and so the natural log of e, well, I'll write it in here in this example just so that we see it. Multiplied by the derivative of that something. And so now let's peel that back. So it's e to the sine of x times the natural log of e times now the derivative of sine x, which will be cosine x. Oh yeah, if it's sine of 7x, then it would be you'd have a sine of 7x, you'd have cosine of 7x times by 7 yet. Absolutely. All right, so the derivative is natural log of e basically wipes out. I would probably leave the cosine of x at the end, and so put here e to the sine x cos x. And again, maybe like to put the brackets around the x, depending upon how small your writing is getting. So what? Almost like I know, yes. I see, yes. Okay. All right, last one that we'll do. And if you're interested in kind of, the last two examples, so that when you're doing your homework, you know that you can go to, well, actually, maybe either of the 2 semesters from last year. Not on School Zone. You actually have to go to my website link. And so if you go to, you can get to it through School Zone. Right? It's there under the resources. It's like, it just says Mr. Garkey's website. Go there. And anybody not seen that? Like, no clue what I'm talking about? Okay. Do you want to know where it is? Kind of, yeah? Because this would be helpful. Because this is the last one we'll do. Because as I've said, you've got the rest of the tools. So you could do this one on your own. Or you could do this one on your own. And so if you want to do it and you want to see, well, what does it look like? Or if you just want to go find it and print it off, right? You can start through School Zone. So I'll just quickly show you. School Zone. And you log in with your own. And then go to the Resources tab. Go to, this is Math 31. And this number 3, the sites.google.com. If you go there, right, it shows my website, and what you're going to be looking for is under the Math 31. If you go to semester 1 from 2013-2014, oh, actually don't, because you can access the PDF notes somewhere through here. Apparently not. Huh. These ones aren't active. Here. Go semester 2. Go semester 2. There we go. Logs and exponents. And then, oh, so this is actually deriving exponential functions. This is the last example, the video of the last example. And then these are the notes. The same notes that you're taking, basically, but at least they're already done. Okay, so if you want to go there. This is where you can go. 2014, 2015, semester 1. This is where you can go, obviously, for these ones. In fact, these are the trig ones. These are the ones we just did. Right? So those you can access. So that way you can go and do these last 2 big examples, or at least see them done if you're interested. But we're gonna finish off with this example here. I'm about to do this one. Right? Yeah, and then that way you've got some time that you can work instead. You got stuck on this one? You haven't tried it. That's e to the y minus 2 on the bottom? Yes. Yeah. Nice job. Whew. take the rest of the day off. Well, maybe not. Not quite. Okay. With this example, of course, you look at it and you go, well, wait a minute. I've got two y's. All right. So that means I need to derive implicitly. All right. So I'm going to derive with respect to x. And if you derive with respect to x, if I start on the left-hand side, what's the derivative of e to the anything with respect to x? It's e to the anything multiplied by the natural log of that base. So natural log of e is just 1, multiplied by the derivative of that thing. So this is where our dy dx comes from. And then on the right-hand side, if you derive 3x with respect to x, you get 3. And then if you derive 2y with respect to x, you get 2 times the derivative of y with respect to x. And so we've got two places there that we see the dy dx, so we need to kind of get them together, factor it out, and go from there. So again, kind of a couple different ways that you can do it. Personally, I'm going to move the dy dx's to the left-hand side because the 3 is kind of already positive on that right-hand side. So e to the y dy dx minus 2 dy dx is equal to 3. Factoring out dy dx, we're going to get e to excuse me, e to the y minus 2, and that's equal to 3. And so our derivative, and if you want, you can shorten that to just be y primed, is equal to 3 over e to the y minus 2. Okay. All right, so those last two examples, as I say, they're kind of just continuing on using the same kind of tools that we've used before. I would encourage you sometime over the weekend even to have a look at the last example, and if you're unsure of anything, please feel free to ask. Tomorrow we'll look at the derivatives of logarithmic functions. And again, we'll kind of spend a little bit of time, not as much time, because it doesn't take quite as long. And then tomorrow we'll hopefully get a little more time working with, you know, finding the equation of a tangent and this kind of stuff. Okay?